Hi, this is Dr. John Bergdorf. In this video, we're going to be looking at some logarithmic equations. In other words, equations in which variables are inside logarithmic functions. And in particular, we're going to focus on logarithmic equations that involve more than one logarithm. Here is the key idea that we want to hold on to. What you want to do is use properties of logarithms to write each side of the equation as a single logarithm with a coefficient of 1. Now, the logarithms on each side must have the same base. If you have a base 8 logarithm on one side and a base 14 logarithm on the other side, all bets are off. We're not going to look at those. Here's a good example. Logarithm base 8 of x minus 3 plus logarithm base 8 of x minus 4 equals logarithm base 8 of 20. So what I'm going to do is I'm going to try to combine the logarithms on the left so that I have one logarithm on each side with a coefficient of 1. And here is where we remember some of our properties of logarithms. This is an important one, for example, that the logarithm base b of a product is the logarithm of the first factor plus the logarithm of the second factor. Logarithms of products split up into sums. Taking that property and reading it backwards, we see that on the left side you could actually combine these two logarithms like this. The logarithm base 8 of, and taking the sum and combining them into a product, x minus 3 times x minus 4. And this achieves exactly the goal that we want to have of a single logarithm on each side. Now we're going to use the fact that logarithmic functions are one-to-one to observe that the only way that the values of these two logarithmic expressions could be the same is if the quantities inside the logarithms were themselves equal. So we're not really like dividing out a log base 8 on either side as if it was like a number. We're observing that the quantity inside the functions must be equal in order for the function values to be equal. But that said, it's very simply that if the logarithm on the left equals the logarithm on the right and they have the same base, then the quantities inside the logarithms must be equal. And that's the goal you want to try to achieve. Once you do that, you will have created most likely an equation that's similar in form to equations that you've seen many, many times before. In this case, this is a quadratic equation, and we can solve this by simply multiplying the polynomials on the left and then applying techniques that we know about quadratic equations. So let's begin by using the FOIL rule on the left side of the equation. The product of the first terms is x squared. The outer product is minus 4x. The inner product is minus 3x. And the last product, negative 3 times negative 4, is 12, equals 20. Going to the next slide, we combine the like terms, x squared minus 7x plus 12 equals 20. Subtract 20 from both sides. This is all very familiar territory. So 12 minus 20 is negative 8. And then maybe the polynomial that is in front of us now will factor, and it does. Factors is x minus 8 times x plus 1. Set each factor equal to 0. And we get two values for x, 8 and negative 1. And you might think at this point, okay, I'm done. Those are my solutions. But there's a very important fact to remember. And we've said this in many ways, but the simplest and most casual way to say it is you can only take logarithms of positive numbers. Now, does that mean that anytime you get a negative number, you should throw it away? Not necessarily. What you want to do is you want to look back at the equation the way it was originally written and ask yourself if I substitute these values of x into that original equation, would I be taking a logarithm of something other than a positive number? Here was the original equation again, just writing it down one more time. It was logarithm base 8 of x minus 3 plus logarithm base 8 of x minus 4 equals logarithm base 8 of 20. And the problem actually really is going to be with this negative 1. If I take the value negative 1 and substitute it into those two logarithmic expressions, notice I'd have logarithm base 8 of negative 4 and logarithm base 8 of negative 5. Those would both be undefined. What that means is that solving logarithmic equations can generate false solutions. This is the only thing you have to worry about, though, that you can only take logarithms of positive numbers. If you're okay with that, then the solution is okay. This negative 1 is a false solution. We throw it away. What about the 8? Well, if we substitute the 8 into the original equation, we end up with a logarithm base 8 of 5 and a logarithm base 8 of 4. That is not a problem. I'm not taking a logarithm of a negative number. I'm taking only logarithms of positive numbers. That's perfectly acceptable. That is actually the only checking that I have to do. So the solution set of this equation contains 8. And that's a nice example. Here's another example, and there's a couple things to point out. First of all, on the left side, we have a subtraction of logarithms instead of an addition. And on the right side, there's not a logarithm at all. My goal was to have a single logarithm on each side of the equation with a coefficient of 1, and there's no logarithm on the right at all. There's several ways that this particular issue can be handled. Here's one that I like. We have a property that says the logarithm base a of itself is equal to 1. And I used b as the base on the previous example, but we've been using a more often. Let me go back to that. Doesn't really matter. Here's what you could do. On the right side of the equation, write that 2 as 2 times 1, and then replace the 1 by using this theorem. Now, what do you use for a? Well, what you simply do is you make sure that the base of the logarithm is consistent across the entire equation, because this will not work unless the bases are all the same. So because on the left side of the equation I'm looking at log base 3, I want to let a be 3 in this expression, so I would have logarithm base 3 x plus 5 minus logarithm base 3 x minus 3 equals 2 times, and then I'm going to replace the 1 by logarithm 3 of 3. Simple replacement, but it gets me a logarithm on each side. Now, what I want on each side is a single logarithm. On the left, I've got 2, so I'm going to need to remember another one of my logarithm properties, and that one says that the logarithm base a, again, I'm going to switch back to a, of a quotient of 2 expressions can split up into a logarithm of differences, a difference of logarithms, rather. Read that property backwards, and we see that the difference of the 2 logarithms can be rewritten as a logarithm of a quotient, thus getting me a single logarithm. It'd be x plus 5 over x minus 3. What about the logarithm on the right? Well, there's another property that I like that says that if you have a logarithm base a of something to a power, the power can be brought down up front as a coefficient. Reading that one backwards, the coefficient can be essentially brought back up as an exponent, so the right side of this equation can be written as logarithm base 3 of 3 squared. So I'm cleverly using different properties of logarithms that I have, but the end goal is a single logarithm on each side with a coefficient of 1. I didn't want that 2 sitting in front of it. And if these two logarithms are equal, then the quantities inside the logarithms must be equal. Again, that's that one-to-one notion. So I set x plus 5 over x minus 3 equal to 3 squared. And then I just make sure that I know what to do with that. This is actually a fairly simple example of a rational expression, a rational equation. We like to see if we can get rid of the fractions in these. Tell you what, let me do one thing. 3 squared is 9. It is perfectly legal to multiply both sides of an equation by the same quantity. So if I multiply both sides by x minus 3, the x minus 3's divide on this side, and I will get x plus 5 equals 9 times x minus 3. Linear equation, I should be able to handle that. Let's see where this will take us. X plus 5 equals 9x minus 27, distributing that out. Suppose, just to keep all the coefficients positive, we add 27 to both sides. And subtract x. So again, whatever we do on one side of the equation, we do on the other side as well to keep to get an equivalent equation. The x's would add to 0 on the left. The 27s would add to 0 on the right. And then we do a little bit of arithmetic. 5 plus 27 is 32, is equal to 9x minus x, 8x. Divide both sides by 8, and I get a 4. 4 equals x. Is that a legitimate solution? Looking back at the equation again, it was this. Logarithm base 3 of x plus 5 minus logarithm base 3 of x minus 3 equals 2. And the only goal is to make sure that when I take this value of x and substitute it into the equation, that I'll be looking at the logarithm of a positive number. 4 plus 5 is 9, 4 minus 3 is 1. Those are logarithms of positive numbers. That means this is a fine solution, and the solution set consists of 4. Let's look at one more example, and this one, although it looks innocent enough, actually is going to get a little bit ugly, but it's good practice for that reason. Notice that once again we have two logarithms on one side and no logarithms at all on the other side. Let's replace that 1, first of all, by a logarithm using that same property that the logarithm base a of itself is always 1. What's the a? You match the base with the existing terms that you already have, so that's going to be a 7. On the left side, the logarithm of the product, let's go ahead and combine those. The sum of the logarithms, rather, becomes a logarithm of a product, so I can write that as a single logarithm like that. On the other side, replace the 1 with the log base 7 of 7, so that I've got a logarithm on each side. Set the quantities inside the logarithms equal to each other. X plus 2 times x plus 9 equals 7. Still looks good. This is a quadratic equation again, like example 1 was, so let's multiply this out by the FOIL rule. X squared plus 9x plus 2x plus 18 equals 7. Combine like terms and subtract the 7 from both sides. X squared plus 11x plus 11 equals 0. Now, in example 1, we got something that factored, but this polynomial, if you stare at it for a while, you'll realize that it doesn't factor. Going way, way back, that's not the only way that we necessarily have for solving a quadratic equation. We have our old friend also, the quadratic formula, that we have used many, many times. With my A would be 1 and B and C would both be 11. Let's go to another slide and see what that would look like. So x squared plus 11x plus 11 equals 0. This is my A. My A is 1. This is my B. This is my C. X is equal to negative B plus or minus the square root of B squared minus 4 times A times C, all divided by 2 times A. That's multiplication. Simplifying a bit, we'd have negative 11 plus or minus the square root of 121 minus 44 all over 2. Then 121 minus 44 is 77. So the square root of 77. Now, in general, we really like to leave our answers in exact form, rather than decimal form. So we would like our answers to be of this form. We could stop here if this were not a logarithmic equation, but we have to worry about whether we're going to be looking at a logarithm of a positive number or a non-positive number. And really the only way that I can handle that is to get my calculator out and get an approximation for the two solutions that exist here. One of them would be negative 11 plus the square root of 77 over 2. The other would be negative 11 minus the square root of 77 over 2. Now, punching these into my calculator, which I've done off to the side over here, the first one is approximately negative 1.113, rounded to the nearest thousandth. And the second one is approximately negative 9.887. Now, since the issue is we only want to take logarithms of positive numbers, at first glance you might say, oh, look, these are negative, so I need to throw them both out. But we need to be a little bit careful. Let's go back or let me just rewrite the equation as it originally stood. So logarithm base 7 of x plus 2 plus logarithm base 7 of x plus 9 equals 1. The approximations to our two solutions are negative 1.113 and negative 9.887. I want to look at the first one of these particularly. It is a negative number, but when you substitute it into the equation, negative 1.113 plus 2 is going to be positive, and that's fine. If I plug it into the second logarithmic expression, negative 1.113 plus 9 is positive, and that's fine. I'm taking logarithms of positive numbers, so this is in fact a legitimate solution. And I want to include that one. To be exact, in the exact form, what this was negative 11 plus the square root of 77 over 2. So I want to keep that one. Looking at the other potential solution, though, which is also a negative number, when I plug that in to logarithm x plus 2, that's going to still be a logarithm of a negative, which is undefined. That's bad enough. We would have to stop right there. But it is also true that if I substitute negative 9.887 for this value of x, you'd also be looking at the logarithm of a negative number. And we can't have that. This is the one that came from negative 11 minus the square root of 77 over 2, which algebraically, as we solved it, there's nothing wrong in what we did. But when we come to the end, we have to realize that that is a false solution and we have to throw it away. Therefore, our solution set consists of only negative 11 plus the square root of 77 over 2. And there you have three very nice examples of logarithmic equations that have more than one logarithm in them.